Okay, problems. F of x is equal to 2 plus x minus 1 whole power 2 by 3 in the closed interval 0, comma 2. You check whether this function satisfies Rolle's theorem. Solution: given f of x 2 plus of x minus 1 whole power 2 by 3 in the given interval 0, comma 2. Differentiate it. 2 by 3 x minus 1 power 2 by 3 minus 1, that is minus 1 over 3. We can rewrite this as, so clearly f of x is not differentiable at x is equal to 1, because if you put x is equal to 1, 1 minus 1 is 0, 1 over 0, infinity, does not exist. Therefore, Rolle's theorem is not differentiable. Therefore, Rolle's theorem is not satisfied. Next question. Let C0 by n plus 1 plus C1 by n plus C2 by n minus 1 plus dot 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 Cn minus 1 by 2 plus Cn is equal to 0. Show that function C0 x bar n plus C1 x bar n minus 1 plus dot 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 Cn vanish at least once in the open interval 0, 1. Prove. Define phi of x is equal to C0 x bar n plus 1 by n plus 1 plus C1 x bar n by n plus dot 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 Cn x in closed interval 0, 1. First condition, phi of x is continuous in a closed interval AB. Second condition, phi of x is differentiable in open interval AB. Phi dash of x is equal to C0 n plus 1 x bar n by n plus 1 plus C1 n x bar n minus 1 by n plus dot 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 Cn of 1. Cancel it. So you are left with C0 x bar n plus C1 x bar n minus 1 plus dot 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 Cn of 1. That is third condition. Phi of 0, C0 0 bar n plus 1 by n plus 1 plus C1 0 bar n by n plus dot 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 plus Cn of 0, that is 0. Similarly, phi of 1, C0 1 bar n plus 1 by n plus 1 plus C1 1 bar n by n plus up to Cn of 1, that is C0 by n plus 1 plus C1 by n plus Cn, that is 0. So phi of 0 is equal to phi of 1. All conditions of Rolle's theorem are satisfied in between 0 and 1. So by Rolle's theorem, there exists a real C such that phi dash of C is equal to 0, that is C0 C bar n plus C1 C bar n minus 1 plus dot 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 plus Cn is equal to 0. So it vanish if x is equal to C, where C lies between 0 and 1. Okay, that's it. Next problem. C0 up to Cn are real numbers such that C0 plus C1 by 2 plus C2 by 3 plus dot 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 plus Cn by n plus 1 is equal to 0. Then show that equation C0 plus C1x plus C2x square plus dot 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 plus Cn x bar n is equal to 0 has value between 0 and 1. Proof. Define phi of x is equal to C0 x plus C1 x square by 2 plus C2 x cube by 3 plus dot 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 plus Cn x bar n plus 1 by n plus 1. in the closed interval 0, 1. So first one, phi of x is continuous in the closed interval 0, 1. Phi of x is differentiable in open interval 0, 1. Phi dash of x c naught of 1 plus c1 2x by 2 plus c2 3x square by 3 up to cn n plus 1 x bar n by n plus 1. So cancel it, n plus 1, n plus 1, 3, 3 cancel, and 2 with 2 get cancel. C0 plus C1 x plus C2 x square up to Cn x bar n. Okay. Third condition, phi of 0, C0 of 0 plus C1 of 0 plus C2 of 0 up to Cn of 0, that is 0. Phi of 1, C0 of 1 plus C1 of 1 plus C2 of 1 by 3 plus Cn 1 bar n plus 1 by n plus 1. So we are left with C0 plus C1 by 2 plus C2 by 3 up to Cn by n plus 1. So 0, both satisfy. Phi of 0 is equal to phi of 1. All conditions of Rolle's theorem are satisfied. So by Rolle's theorem, there exists real C in between 0 and 1 such that f dash of C is equal to 0, that is C0 plus C1C plus C2C square up to Cn C bar n is equal to 0, C0 plus C1x plus C2x square up to Cn x bar n is equal to 0 vanish if x is equal to C, whenever C lies between 0 and 1. So C is root of this C0 plus C1x up to Cn x bar n in between 0 and 1. Next, let us discuss Lagrange's mean value theorem. Lagrange's mean value theorem. If f of x is continuous in a closed interval AB, f of x is differentiable in open interval AB, then there exists a real C in between A and B satisfying the condition f dash of C is equal to f of B minus f of A whole divided by B minus A. Define A constant has f of B minus f of A whole divided by B minus A. Now replaced A by f dash of C. Okay, that's all. Define phi of x, that is f of x minus f of A minus A times of x minus A in the closed interval AB. So first condition, f of x is continuous in a closed interval AB. Phi of x should be continuous in a closed interval AB. Second one, f of x is differentiable in closed interval AB. Sorry, it is open interval. Okay. So phi of x also should be differentiable in open interval AB. Phi dash of x is nothing but f dash of x minus 0 minus A times of 1 minus 0. That is phi dash of x is nothing but f dash of x minus A of 1, that is A. Third condition, phi of A, that is f of A minus A times A minus A, you get 0. So you are left with f of A minus f of A minus A times of A minus A. This and this get cancelled and A minus A is 0. 0 into anything is 0. So answer is 0. Next, phi of B, f of B minus f of A minus A times of B minus A. That is f of B minus f of A minus, we know A is this, f of B minus f of A In the definition we have mentioned it of b minus a. So it is f of b minus f of a minus f of b. This and this get cancelled. Minus plus. So plus minus minus plus. Answer is 0. So phi of a is equal to phi of b. All conditions of Rolle's theorem. So all conditions of Rolle's mean value theorem is satisfied. So by Lagrange's mean value theorem, there exists real C in between A and B such that phi dash of C is equal to 0, that is f dash of C minus A is equal to 0, f dash of C shift minus A to other side, that is plus A. So f dash of C is nothing but f of B minus f of A whole divided by B minus A. You are done with the proof.